Hello, and welcome back to this series on quantum mechanics. In this video, I will try to explain some of the features of quantum mechanics that we discussed in some general detail in the last video. We start with this question. This very profound yet simple looking question that asks, what does the word quantum mean? All right. So, in a linguistic sense, quantum is derived from the word that means discrete or discrete chunks. All right. So this was first used in the context of quanta, and quanta just means, discrete chunks or packets of energy. What is the physical context to this? Well, if you just analyze a classical mechanics problem, let's say you are skating down a hill. Let's say this is pretty high. It is from ground to top. It is what 3.3 meters or something like that, and you and the skateboard together have a combined mass of 75 kilograms. Okay, and sorry, let's make the mass a little bit smaller, and you basically just roll down this ramp. When you start your journey, basically that potential energy that you have due to the height gets converted to kinetic energy as you start moving. So how much potential energy can you have? So we can calculate that very easily. Use the potential energy, gravitational potential energies, mgh. M is the mass, which is 45 kilograms. And then g is 9.8, let's say, the gravitational acceleration. And h is the height that you started from, which is 3.3 meters. And this comes out to be 1455.3 joules. Okay. All right. You say that's pretty easy, and I agree with you. And there's no problem with it. Okay. And depending on the mass and height, this can be any number possible. All right. This can be any different amount of energy that is converted to kinetic energy as you roll down the ramp. However, that is not true in quantum mechanics, not true in QM. Okay. And quantities like energy, angular momentum, are quantized. That means they are discretized. They only come in specific chunks, okay, or specific values in this context. What is a famous example that I can give you? The most famous example that I can think of is the electron charge, okay? So electron or electric charge. Let's say electric charge, okay? And electric charge for any object is denoted with a Q, is some multiple of the basic charge unit, that is electron charge denoted with a small e, and some multiple is n. All right. So this n is an integer, meaning whole number, and this e is one unit of electron or one electron charge. Okay, so this is the basic unit of electric charge, one electron charge. Correct. So this implies you can have any electric charge. Let's say Q is 2 times E. That means you have a charge worth of 2 electrons, or Q is equal to 937 times E. You have 937 electron worth of charge for the object, and so on and so forth. Okay, but you can never have something like 2.2 electrons. That is not going to be the case. Nor can you have something like 936.5 electron. That can also never be true. Okay, so why electric charge is integer multiples of The electron charge is an open question yet, so we still don't have a very good answer to it. All of our experiments show that this works, and so we take this idea and run with it at this point. Okay, now let's try and explain it in context of quantum mechanics the best we can. So the quantization of electric charge, as we said, is not obvious because you look at your basic electrodynamics course or ENM, and your teacher starts off the class with a sphere of some charge. So you can have sphere of charge, let's say Q is equal to 4.806 coulomb. So you look at me and say, okay, this is not uh, supported by this observation that these are not possible. These values are not possible. It seems to be perfectly fine that macroscopic objects like a sphere can have a charge that is 4.806 coulomb. So does it mean this has 4.806 worth of electrons? Well, not really, because this is just an illusion. Okay, why is that? Because electrons are particles, right? So they are chunky stuff with different mass. So you can never have 1.5 electrons or 1.8 of an electron. That does not really work. You either have one electron or two electron, nothing in between. So what is this? What does this mean then? Well, this is an illusion because if you work it out, this Q of 4.806 coulomb is nothing but actually approximately 3000 times 10 to the 16 electrons. So basically, you take the electron charge. If you remember the electron charge, this is 1.6 times 10 to the minus 19 coulombs. There are 10 to the 16 electrons in this charge, and you multiply by 3000. That is basically what comes out to 4.806. But then this doesn't seem very discrete. So on the face of it, it seems like it can be any factor. It is not uh, only 4.806, it can be 4.807 or whatever. Is that really true? Well, it becomes obvious that this is not true when you increase the precision of your calculation. So if you are very precise to many, many decimal places, you find, okay, the original charge Q is 4.806. That's fine, but that's only 3 decimal places. Let's go higher. We will find 529, 862, 39999, 555, 694, and so on. Okay, and now to this charge, if you add one extra electron, so Q plus one extra electron will then be 4.806529. So still no change. 86239999555, still no change. But then the last three digits that we're in our position, because this keeps going on, in our position, this becomes 854. So the transition between adding one electron and the previous charge is a discrete change. So if you look at charges at very high precisions, it becomes obvious that actually charges come in discrete amounts, because the change between the charges, if you are very precise, happens to be always discrete amounts. That makes sense because electrons are particles, chunky things, which can either come as a whole or two electrons or three electrons and never come in halves or three halves. What does this mean in the context of quantum mechanics? Well, a similar observation really holds if you look at electron in a hydrogen atom. So what is the hydrogen atom anyway? Well, it has a nucleus with one proton, and then surrounding it, let's say we're observing the Bohr model, which is obsolete, but okay, it works in this context. Well, you have one electron here. That's it, right? However, that's not the only energy level or orbit, as Bohr would say, that the electron can reside in. Essentially, the electron, this is the proton here, the electron can be in this in this orbit close to the nucleus, or in this orbit a little bit farther away, or in this orbit a little bit more farther away, and basically can make transitions between energy levels, right? So electron can jump to this energy level, and then come back down to its original energy level, and this transition emits photons, that is light, right? And we can measure that wavelength of light, and that measurement of the wavelength of light that is emitted every time an excited electron falls back to its original level tells us that every time electron makes a transition, the transition energies are fixed. Okay, so that means you can always measure, let's say this is n equals 1, the first energy level, this is n equals 2, the second energy level. You can always measure the transition between n equals 2 and n equals 1 as the electron falls back from n equal 2 and n equal 1, emitting a photon. You can always measure this transition, you will always get the same number. That means the electron can never fall, let's say, halfway in between n equals 1 and n equals 2. That is never going to be true. And this tells me that electron energy levels are quantized. That means they can only be some discrete numbers. But nothing in classical electromagnetism tells me that this has to be the case. So in classical electromagnetism, there is no restriction to the fact that you can have energy level 1, energy level 1.5, energy level 2.5, or energy level 3. There is no restriction to why that cannot be true. Okay, so that is in the context of quantum mechanics, fundamental quantities like energy is quantized. Okay, and this is the idea of quantum jumps. As the electron shifts energy levels, we say that they're jumping from one energy level to the other, and these quantum jumps always occur in discrete steps. Okay.